In this video, we're going to take an introductory look at this concept of recursion. So recursion is a type of problem-solving strategy or problem-solving technique that goes about reducing larger problems into smaller problems of the same form. And it's a very important strategy or technique to master as a computer scientist because there's a lot of problems that exist that may be very difficult to solve without using a recursive strategy. And if you're able to apply an appropriate recursive strategy, then the problem becomes maybe very easy to solve, assuming that you can get the recursive solution correct. So I have some pictures here of some recursive structures that you may find in nature. So we have a picture of a shell here. This is just a picture of a cabbage, but it's been zoomed in on a tree, and these are just ice crystals. And in each one of these structures, we see a larger structure that's composed of smaller structures that have the same form. So these pictures probably don't provide much of an insight in terms of what's going on and how you go about devising a recursive solution, but it's pretty cool to see that these recursive structures actually exist in nature. So what about devising a recursive solution? There's really two parts to it. One is identifying a base case, or what we call a simple case, that we can solve easily. And the other is identifying a recursive case, and the recursive case needs to be breaking our problem down into a smaller problem of the same form. And if we're not doing that, we will not be converging toward that base case. So it's very important that this recursive case here, on each time that we do it, it's converging toward this base case. Otherwise, we would never actually exit our recursive solution. We just keep on going. And we probably don't want to do that. So there's a lot of programming languages that support this idea of recursion, and they support it by allowing functions to be defined in terms of themselves. So what that means is we can write a function definition, and in that function definition, we can have a call to that same function. So that's how programming languages go about supporting this idea of recursion. And it should be noted that not all programming languages have support for recursion, so they do not allow you to have a function that can be defined in terms of itself. So let's take a look at a general structure of a recursive function. And whenever you devise a recursive function, it may not follow this structure exactly, but I think it's a good idea to have this in the back of your mind. So you may have an if statement to test for a base case, and if that base case turns out to be true, we can just calculate or evaluate the base case. So that should be something that's very easy to solve without doing a recursive call. Otherwise, you're in the recursive case where you're going to be breaking down that problem into a smaller problem of the same form. So you need to be converging toward that base case. So this is going to require doing a recursive call, and you'll continue doing those recursive calls until you finally end up at this base case. And it should also be noted that here in the recursive case, that these smaller solutions that we're devising on every single recursive call is going to be used to solve the larger problem. So it's this divide and conquer technique that we're trying to use. So I guess I should point out that the recursive strategy is a divide and conquer strategy. So there's different forms of divide and conquer, and doing recursion is one of them, where we're just kind of breaking these problems down and solving these smaller problems, and then being able to combine these smaller solutions to solve a larger problem. So let's take a look at an example where we can use recursion. And one of the classic examples is the example of factorial. So we can use recursion or the recursion strategy to get the factorial of any particular number. So let's just go over and kind of review this idea of factorial. So if we were to say 4 factorial, what that means is 4 factorial is equal to 4 times 3 times 2 times 1, which is 24. But we could also define 4 factorial recursively by breaking it into a smaller problem of the same form. What do I mean by that? Well, we could say 4 factorial is just simply the value of 4 times 3 factorial. So we've created a recursive part here. So we've got this part here that's a smaller form of our original form. So this was our original problem where we wanted to calculate 4 factorial, which we know how to calculate, but we could define it recursively by just saying 4 times 3 factorial. And then we could say, well, 3 factorial could be defined as 3 times 2 factorial. So this was the recursive part here, or the recursive case, and we've just taken it and broken it down into a smaller form of the same problem where we have 2 factorial. And then we have 2 factorial, which is just 2 times 1 factorial, and 1 factorial is just 1 times 0 factorial. and we have a fact of 0 factorial. So this would be our base case here of 0 factorial being 1. So if you're uncomfortable with this idea of 0 factorial being 1, or just accepting that that's the case, then you may want to do a Google search for empty product, and it will discuss in a little bit more detail of why if you have a series of products and you have an empty product, meaning you have nothing there, which is effectively what we're doing here. We have a series of products here, and in the case of the 0 product, we're saying that nothing is there, and so we just want to have the identity value, or the value of 1 in that particular case. But if you go and search for empty product, you'll probably get a better explanation than what I was able to do just in those few seconds. So now what we've done here is we really have created a recursive solution, or a specific recursive solution in this particular case. But we could generalize this a little bit more, and we could say that the recursive case, so for n factorial, we could define the recursive part is just simply n, so whatever the value is, times n minus 1 factorial. And that's what we had in each one of these cases here. 4 factorial, so 4 times 3 minus 1, 4 minus 1, which would be 3, so that'd be 4 times 3 factorial. So that's the case all along here. So this is really the recursive part. And mathematicians actually define factorial using this here. So this is the formal definition of factorial. So if we have n factorial, if n turns out to be 0, we know that that's 1. If it turns out that n is greater than 0, then we just simply have n times n minus 1 factorial. So let's use this information here. So this really defines our base case, and this defines our recursive case, and go and implement this as a recursive function in C++. So let's go over to Eclipse and implement this. Alright, so I have Eclipse loaded up, and I've already created a project called Factorial and created a factorial.cpp file within that project. And I also have a pound include for IOStream and the using namespace standard statement. So let's go ahead and write our factorial function in a recursive manner. So this function is going to return the factorial of some particular inputted value. So if we put in 4, then it's going to return the value of 24, since the 4 factorial is 24. So it's going to be an int returning function, and we're going to just call it fact for factorial, and we'll pass in an int value, and we'll just call that int value n. And so inside the body of this function, we'll have our base case and we'll have a recursive case. So the base case is whenever we have n being equal to 0. So if n is 0, 0 factorial, we know what that is. That's in fact 1. So we can test for that. We can test to see if we are in the base case. So we can test to see if n is equal to 0. And if that turns out to be the case, then we'll just simply return the value of 1. So the user could pass in the value of 0 there. Otherwise, else, we're in our recursive case. And we said here for the recursive case, they would have n times n minus 1, and we would say n minus 1 factorial. So I'm going to just use the exclamation point, even though it doesn't make any sense here in C++, because we have that exclamation point for the not operator. But that's what we're trying to do. That's our pseudocode, I guess you could say. And the pseudocode is almost the right code that we need to have. What we need to do is we need to have n minus 1 factorial. Well, we're writing the factorial function, so that what we'll do is have a recursive call here. So this will just be fact, calculating the factorial of n minus 1. So we'll have this business here. And what we'll want to do is return the result of this. Now what's interesting is say the user passes in the value of 4. So the value of 4 gets passed in here, and then we would have 4 is not obviously equal to 0, so this is not true. And so we come down here and have 4 times, and then we have another function call. So this return is not going to be able to complete until we go all the way through all those function calls, and we finally get down to n being equal to 0. At that point we can return the value of 1 and start unwinding from all of those function calls. So what's really going on here is every single time that we have a function call, we have a brand new stack frame being pushed on the stack. And I think I'll spend some time in a video, in a later video, in which we'll look at all these function calls and draw out the stack frame to see exactly what's going on with these recursive calls. Because if you can picture what's going on with a stack, it makes recursion a lot less mystical or magical in terms of what's going on. So that's our recursive function there for calculating factorial. So if that's a little bit confusing, that's okay. Maybe it should be confusing at this point, but I just wanted to kind of illustrate how we go about devising a recursive function. We have to have that base case, and we have to have a recursive case that is in fact converging down toward the base case. So let's go ahead and write a main function and test this code out. So we'll say int main, and then inside the body here we'll say that we will declare a variable for an int variable for num that will hold the number that the user inputs, and then we'll say maybe cout, and do we'll say enter a number to calculate the factorial of, let's see, and we'll do an endl here. We'll read that value in using cn, so cn that particular value, and then we'll do another cout and just call our fact, passing in the value of num, and we'll do an endl here. So let's go ahead and save that and build it, see if it builds okay. It looks like everything is building okay, and now we'll run it. So let's go ahead and test this out with the value of 4, because we know what the factorial of 4 is. It should be 24, and yeah, that's exactly what we get. Alright, so just to wrap up this video, I wanted to say that recursion is one of these areas of computer science that's often difficult to master. It just takes some time and practice. And I think the reason why it's so difficult, or often poses a difficult challenge to people, including myself, is that it's not the way we think. We don't think in a recursive manner in general. We think in a looping manner or an iterative manner. And it turns out that for a lot of problems, we can solve those problems using an iterative approach, or we could use a recursive approach. And it may be the case that there's not a whole lot of difference in terms of the amount of work that's being done by the computer with an iterative approach or a recursive approach. But in other cases, it really does depend on, the implementation we have. So we may have a very bad iterative implementation or a very bad recursive implementation that would cause the computer to have to do a lot of work. Now, there are problems in which you really should be using a recursive approach, because the iterative approach would be just so difficult and unwieldy to even try to implement, that the recursive solution is very elegant in contrast. So just know that it does take time to often come up with a recursive solution for a particular problem. Sometimes it may be, a few minutes that you spend, but often it will be maybe a few hours or even a couple of days that you may think about a recursive solution before it dawns on you in terms of what you should be doing. So in the next video, we're going to be looking at what's going on with the call stack. So I think if we examine exactly what's going on each time we do a recursive call, and examining the call stack and looking at the stack frames, it'll sort of demystify what's going on with those recursive calls. So that's it for this video.